So now let's talk about probably the hardest problem in this contest, problem 2. So for this one, I guess let's start by figuring out how do we answer the query without any updates, right? So if we're just given a fixed array where every cow we know who they're going to vote for, and essentially we want to divide the two cows or the cows into two groups, and every cow has to be part of exactly one of your two groups, and both of your groups have to be non-empty. Um, so I guess let's first consider a relatively naive like n squared approach. Right. So how would we try to do this in n squared per query? Right. Well, one possibility is let's just try to figure out is every pair possible? Right. So initially, we'll just try to compute, is it possible to have the cow at index 0 be one of the head cows, and also have the cow at index 1 be one of the head cows? And if that works, then we can also try 0 and 2. We can also try 0 and 3, so on and so forth. And then, of course, we'll also try 1 and 2, 1 and 3, 1 and 4, all the way down to all n squared pairs. Right. And now the question is, for a pair of cows, how do we know if it's possible to separate the two groups such that one of your cows is the most frequent one in one of the groups, and your other cow is the most frequent one in another group? So this depends a lot based on the maximum cap. So let's say you got, let's do an example like this. So here I'm just going to write what cow each cow is voting for. So these are like the cow numbers. And then down here I'll write who they vote for. So let's say this cow is voting for 1. This cow votes for south. This cow is voting for 4, 4, 4. And then this cow is voting for 2. And this cow votes for 3. Okay, so let's take some examples. So first of all, is it possible to have cow 2 and cow 3 be the two head cows? Well, first of all, whatever cows are voting for cow 2 will definitely put into one group, right? So let's go ahead and put this cow. So let's go ahead and put cow 5 into group A. And then we'll put cow 6 into group B, because basically we're gonna have group A, the green group, try to make sure that they're all voting for cow 2, and the red group will have them vote for cow 3. Now, is there a way we can actually distribute the rest of the cows so that cow 2 is in fact the most popular one in the green group? Well, we can try, right? So one possibility might be, okay, let's go ahead and assign cow 0 into green group, and assign cow 1 into red group. So far so good with all these assignments. But then now we think about these cows that are voting for 4. And it turns out no matter how we distribute the groups, they're going to make cow 4 the most popular in one of them, right? So it's like we can put at most one of the cows into green and one of the cows into red. But then the last cow has nowhere to go, because now, regardless of if I assign this cow to be green or red, they're going to make cow 4 the most popular one in that group. So this is how we can figure out that, oh, it is not possible to have cow at index 2 and the cow at index 3 be the most popular cows in their respective groups, no matter how we do the assignment. And it turns out the math behind this becomes relatively straightforward. It's just, let's say you're trying to get cow 2 and cow 3 to be the most popular cows. Then you just need to count how many cows are voting for them. So in this case, 1 each. And now you can just add the two numbers up. And the sum of these two numbers must be greater than or equal to all the other counts, right? So in this case, we have three cows voting for cow 4. That is not less than or equal to this number, and therefore it doesn't work. Okay. So this gives us a n squared algorithm where if we count for every single cow, how many cows are voting for them, and then we loop through each pair and we just check for each pair, it's possible or not, depending on the criteria we just talked about, right? So if you have like A cows voting for like cow 1, and you have B cows voting for cow 2, and you want to make cow 1 and cow 2 your head cows, then this is only possible if A plus B is greater than or equal to max cows. Cool. Now let's talk about some speedups for this, this singular query version. So one idea, or there's a few things to note. The first thing is, if you think about the frequency, meaning how many cows are voting for a specific cow, right? There is at most square root of n distinct possible values, right? So in the worst case, you could have one cow vote for one of the cows, and then two cows will vote for another cow, three cows vote for another cow, and so on and so forth. But you can only get up to roughly square root n before the sum of this is equal to n, right? So the maximum number of distinct values you can have in terms of frequency is only square root n. So now let's go ahead and analyze it based on the frequency buckets, because we know there's only square root n frequencies. So let's say for one of your frequencies, it is equal to A. Now let's do a concrete example here. So let's say the current frequency you're looking at is 3. So basically you think about all the cows that have exactly 3 other cows voting for them. Okay. And let's say the max count in our example here is 7. Then what does that mean? Well, that means for your frequency 3 cows, so the cows getting 3 votes, they must be paired with a cow getting at least 4 votes, right? So the value of B here needs to be at least 4. And as long as you have this, then we know it is possible to divide the groups. Okay, so now how should we pair up cows? Let's go ahead and scroll down a little bit. So let's say you have a cow here, and I'll use black for they get 3 votes. And this denotes like the positions in the array where a cow gets 3 votes. And you also have your green dots, and that means they're getting 4 votes. Okay, so if we want to find the furthest like distance, let me go ahead and do green as greater than or equal to 4. So if you want to do the greatest distance possible, then it turns out you only need to consider the first or the last cow with 3 votes. And the idea is no matter where your black point is in this range. So let's take an example here. So like we have this point, and its furthest green dot is here. But we might as well use this to get a further distance, right? Or similarly, if we're trying to use this point, its furthest green dot is over here. But again, we can just use this point to get an even further distance. So we only need to consider the 2 black dots at the start and at the end. And then from here, now the question is, what's the furthest away green dot from the first black point? And what's the furthest away green dot from the last black point? So now this becomes a data structures problem where basically you have an array of numbers and you want to query like what's the farthest right you can go where the element you end up finding is still greater than or equal to x, right? In this example, x being 4. Okay, so how do we do this? There's a few possibilities. A kind of straightforward approach would be to use some sort of range max query, right? So let's give an example. So let's say the array here is this is 3, this is 3, this is 3, this is 3, this is 3. And let's say this is 5, this is 2, this is 1, this is 6. Let's say this point is 5, this point is 4, and you have like a 2 and a 2. Okay, so let's say this is our actual array, and again, all the black points represent frequency 3, like 3 votes, and then all of the green points are at least 4 votes, right? So if I want to know for this black dot, what's the furthest green dot to the right we can pair it with, then one idea is, well, what if I can query for the suffix max, right? And I can just binary search on the suffix max. So the suffix max in this portion of the array, so we're binary searching, so we ask, is it possible to go up to the middle point? And the answer is yes, we can go to the middle point because there is a value here that is greater than or equal to 4, right? The range max here is 5. Okay, and then we can binary search to this range and we say, okay, this is still 4. So we know within this range, it still works, right? Cool. So basically, whenever you binary search on a suffix and it works, you can just decrease the suffix, like shrink the range of the suffix, because we're trying to find the furthest right we can go where we still have at least one number be greater than or equal to 4, right? Okay, cool. So we can just do a suffix max query every time, and we'll binary search to find that this is the furthest to the right you can go and still find a number greater than or equal to 4 within that suffix. And cool, so that would be one potential answer. So for this black dot, we would pair it with this green dot, and this can be found in roughly like log n time. Or yeah, so for example, you can just pre-compute suffix max, and then you can binary search on this to find the furthest one to the right. Now you can do something very similar. So for this last black dot, we want to find the furthest left green dot. So now all we need to do is we need to query prefix max. And we can once again binary search for what's the smallest prefix we need, such that we have a value in there greater than or equal to 4. So in this case, we can go all the way here. Yeah, and again, this would just be log n because we just pre-compute like prefix max, and then we can binary search on the latest or the earliest prefix max that has a 4 or greater. Cool. So our current runtime for the solution would be so it would be O of square root n times log n. Right. Because like we discussed, there are a total of square root n distinct frequencies we need to try. And for each frequency, we can find the smallest frequency it can be paired with, and we can binary search to find either the first or last occurrence of that, right? Okay, cool. But this is assuming there's no updates, and therefore we can just pre-compute like a prefix sums or prefix max and a suffix max. Now it turns out if we want to do the original problem, well, first of all, if we just had something like O of Q times square root n times log n, this is fast enough, but you need to be careful about constant factors. Now, the tricky part now is how can we maintain our same algorithm, right? So basically, if we think about our algorithm, we're looping through all of our frequency buckets. And for each frequency bucket, we need to find the first and last one of that exact frequency. We also need to be able to find the first and last element with a value of at least the max frequency minus the current frequency, right? Okay, so there's a few ways you can do this. So I'll present one way using segment trees first. So we can start by computing a range max segment tree. And let's go ahead and do an example of this. So let's just take like a few elements here. So suppose I took the elements like 3, 1, 5, 2. Okay. And I'm just going to compute the max seg tree here. Okay, cool. And now let's say I want to find the first element in my array. So naively, let's think about this as like, if I just go left to right and I scan in this array, and I want to find the first element greater than some value x or greater than or equal to some value x. So of course I can do like a binary search and use range max to answer the binary search, but that'd be like log squared n, which is a little too slow. So the full runtime of that would be like q times square root n times log squared n, which is too slow. So instead, we're going to employ this technique called segment tree walking. So the idea here is, okay, so let's say my target is I want something greater than or equal to 4. Well, okay, I start at this node, and we can say, all right, within this whole subtree, there is in fact something greater than or equal to 4. And how about if we go left? So we look at the left child, and there is in fact something greater than or equal to 4 there, because this stores the max in this array. So we'll go ahead and walk to this 5, and we don't need to consider this part of the tree or this part of the array, because we know we're gonna find something greater than or equal to 4. Specifically, we're gonna find like a 5 if we find the max in this range. Right? Okay, now we try to go to the left again, but we can't go left again because the max in this range is only 3, which is not enough. And therefore, we're forced to go to the right here, and then we can go left, and voila, we found the first element, right? If we scan left to right, the first element that is greater than or equal to 4. And this runs in log n time because we just start at the top of our tree, and then every time we just check the left and right node, we try to go left if possible, and possible just means the left node is greater than or equal to the target we're looking for. And if we can't go left, then we have to go right. And then as long as we follow this process, we'll end up at the bottom, we'll end up at a leaf node that is in fact greater than or equal to 4, and it's guaranteed to be the first element greater than or equal to 4. Okay, we can actually do a very, very similar algorithm if we're trying to find the first element scanning from right to left that is greater than or equal to 4, or any number. Right? So in this case, we're going to prioritize trying to go to the right. So for our example here, we can go to the right because 7 is greater than 4. We try to go right again, and again, it works because 5 is greater than 4. And then we go to the right one more time, because again, 5 is greater than 4. And we end up here, which is in fact the first element. If you scan from right to left, that is greater than 4. So this segment tree walking technique lets us very quickly, in O of log n time, with very good constant factor, find the first or last element that is greater than or equal to some value x. All right. Now, to update this segment tree data structure, it's pretty simple. Whenever a cow changes votes, one of these numbers get decreased and another number gets increased. So basically, you just do 2 update operations on the seg tree. And again, the constant factors here are pretty good because for an update, you just need to walk up the tree. So the log n with good constant is pretty fast for this case. Cool. So this is the first thing we need to be able to query, like, given the current state of our frequency array and given a initial frequency, what frequencies we can pair it with, right? And specifically, we want to pair with the furthest left or furthest right number. So that's part 1. And then we also need to maintain another data structure, which will tell us for every frequency, where is the first and where is the last occurrence of that frequency. Now here, I think you have some leeway or choices for what exactly you want to use. One pretty straightforward approach would just be to maintain a set. So for every single frequency, you maintain a set of indices of cows that have that frequency, right? And now from the set, you could just get the first and last item from the set, which will be the smallest index and the biggest index. And this one's relatively easy to maintain because every single time a cow changes their mind and changes their vote, again, we just need to update this frequency array in 2 positions. One of them is going to get the new element, and one of them, loses an element or an index to be exact. Okay, cool. And that ends up being one working solution as long as you're pretty careful with all your constant factor optimizations. Now, it turns out it is also possible to remove this log n factor. And the way you would do this is with a slightly clever 2-pointer approach. So essentially, if we think about what we're trying to do, we're just trying to find for every singular current frequency what's the first and last. And also, we have this list of valid positions. So these green dots, right? And depending on how you order this, you can basically think of it as you're just adding on green dots. So if you loop from biggest frequency to smallest frequency, then every single time, elements will just turn eligible. So let's say you were initially at frequency 7 and your pairing frequency only needed to be 0. Then initially, or sorry, go the other way. So start with the smallest frequency and go to the biggest frequency. And yeah, as you increase your frequency on your black dots, the frequency requirement for your green dots decreases, which means more elements are available, aka usable as a green dot, as you increase your base frequency. And then from there, you don't need like a segment tree or anything to compute everything, because you're adding on these green dots one by one. So when you add in the green dots, you can just track the min and max. And so that's the general idea for how you can do this with a 2-pointer and remove the lock factor. Okay. Give me a second to set up the third problem. And if you guys have any questions for the second problem, feel free to drop it in the Zoom chat. Okay, is the 2-pointer still O of NQ time? No, if you implement the 2-pointer complete, it will be O of Q times square root n time. So basically you can get rid of this log factor. So this log factor currently comes from both the set query and the segment tree query. But if you iterate in a smart order, you can do those in O of 1 time.